Everyone, in this video we'll go through question 98, validate binary search tree on Leetcode. This is part of our blind 75 playlist on Leetcode where we go through the blind 75 questions. So let's begin. In this question we are given the root of a binary tree and we want to determine if it is a valid binary search tree, BST. A valid BST is one in which if you are given any root, all the items or all the nodes to the left hand side are less than the root, all the items to the right hand side are greater than the root, and the left and right hand side subtrees must also be binary trees. So here we can see that we just have really one level here, or two levels, depending on how you think about it. But if we have the node 2, then on the left hand side we just have one node 1, which is less than, and it doesn't have any children, so we're good. On the right hand side, again, we just have one node, which is a child, and it's a leaf actually, both of these are leaves, and it's greater than, so we're all good. It's true. In the second case, first of all here, we start off at root number 5, and you can see on the left hand side we have 1, which is correct. On the right hand side we have 4, which is not correct because it should be greater than 5. So that's automatically where this fails. Another place that it actually fails is, so just open up Paint, let me paste this in. So we agree that this is basically correct here. This part, 5 and 4, this is not correct, but let's assume that this was something like 8. Let's assume that this was something like 4. Let's assume this was something like 10. Well, if we look at it now, then this part is correct, right? Because the 5 and 8 is correct. This part is also correct. 8 and 10 is also correct. But this 8 and 4, it may look correct, but note that this 4 is actually less than the 5. So it should never be on the right-hand side of the subtree. It should be actually over here or over here. So this is the third point where it says that both left and right-hand side subtrees must also be binary search trees. So that's where it fails. So those are kind of the three conditions we have to look out for. Now, if I just gave you just one root, right? So let's maybe just start off simple. Let's just say that we didn't have any node at all, like it's just empty child, right? Or just empty node. Well, in this case, I think we can automatically return true, right? Because empty node, no node, essentially means that it's a binary search tree. Now, if this is not the case, then we have at least one node, right? So we at least have a tree. So what we can do is we can basically have our recursive helper and we can pass in the root. If you pass in the root, so now we're in a recursive call. So I'll just define it here, root. Now again, let's just say that we run into a scenario where we process the 1, we process the 3, and then we try to process 3's children, and obviously they're both none. If that's the case, then those are valid binary search trees. So if not root again, we'll return true here. Otherwise, so what's kind of the main thing we want to look out for? Well, in a binary search tree, the main thing you kind of want to look out for is the numbers, right? You want to make sure the numbers are less than or greater than a specific amount. So for example, when we are over here, when we are at this node over here, we want this. We want the 4, so we want node to be greater than 5, right? We want it to be greater than 5, greater than the parent's value, and less than whatever the initial less than value was passed in. I think like every single number is going to be less than infinity, right? So in this case, it should be less than infinity. And we can see that this automatically fails this case because although it is less than infinity, it is not greater than 5. So that's why it wouldn't work. Let's assume instead that this value, so we'll keep the values as they were before. So this was, I believe, 8. This we kept as 4. And this we kept as 10. So now let's consider this case. So when we are over here, we want to make sure that 8 is greater than 5 and 8 is less than infinity. And we can see that both of these cases pass. When we are over here on the right-hand side, we want to make sure 10 is greater than 8 and 10 is less than infinity. So both of these cases also pass. But notice here, when we go to the left-hand side, what do we want to make sure of? Well, we want to make sure that 4 is essentially greater than what? Well, it would have to be greater than 5, right? We can't do greater than 8 because we are actually going on the left-hand side over here. If we were going on the left-hand side, then we leave the greater than field what it initially was, which comes from the parent or might come from a few levels up. So in this one, we have to do greater than 5 and 4 is less than 8. We can see that this field passes, this condition passes, but this condition fails. And so that's why this binary search tree will break because it's not a valid binary search tree. So we basically have to check this condition at every single iteration that we're going down, or every single stack frame in the recursive stack. So what about like when we're at the root over here? Like let's just say there's one item, right? What does 5 have to be greater than? Well, if you think about it, if there's just one item, right? All items or all values are greater than negative infinity, and all values are less than positive infinity. So maybe we can start off with this, and depending on whether we go left or right, we will update these greater than or less than values. And then if any of them, at any case, it breaks the condition, then we know that we're not at a valid binary search tree. Otherwise, we'll keep recursing, and if both the left-hand side and right-hand side children are valid, which basically satisfies this, then we know that at least at this position we're valid. And so then we can return to our parent, and then we can go from there. So that's like the basic idea behind this. So let's see how we can put that in code. We already kind of have our like basic template here, but I think I'll need to pass in two more variables here, right? So I'll pass in something like should be less than and should be greater than, right? Or actually, let me maybe just put these as less than or greater than, right? So what's the valid case? Well, the valid case is if root.val is greater than less than and .val is less than greater than. If this is the case, then we know that at this current position, I'm valid. So in this case, I won't actually do anything. But what if we negate this, right? So what if we do not? So if we do not this, then we'll either have that we're greater than the value that we say we're greater than, or we'll say that we're less than the value that we should be. Sorry, it should be the other way. So if this is not the condition, then basically either this one will fail, which means that either the root value will be, this should actually be the reverse. I'm sorry, this should be reverse. Now looking back at it, so let me just start that again. So if root value is less than what it should be less than, and root value is greater than what it should be greater than, if this is the case, then it's valid. If you look back over here, it should be when you're passing in. So what should less than and greater than be here? So less than here will be basically, if we're at this condition here, less than, it should be less than infinity. And greater than, it should be greater than 5. So we can see that if we are greater than 5 and we are less than infinity, then it is a valid case. So if we were to negate this, we consider the case where either one of these fields are false. And so if this is the case, then we can automatically return false. And so that would break out of the recursion. Otherwise what? Well, we need to look at the left-hand side subtree. We need to look at the right-hand side subtree. So let's do that. So we can do left is equal to self.helper, root.left, less than greater than, right is equal to self.helper, root.right, less than greater than. And then basically, assuming these two return the answer we expect, we can do left and right. So basically, as long as the left-hand right and right-hand side are both valid, then we know that my current position is valid. And so then we can return this to the parent. Now, one more thing we have to change here is, well, first of all, we want to pass in left-hand and right-hand side, right? Or less than and greater than. So as we mentioned that for the root, it would make sense that the left-hand side or the less than side, it should be less than infinity, but it should always be greater than negative infinity. So less than, it should be infinity, and greater than, it should be negative infinity. What about when we're going to the left-hand side? Well, if we're going to the left-hand side, then the thing I want is that I want the left-hand child to be less than my current root value, right? So for example, if I'm over here and I'm going to the left, I want 4 to be less than 8. So this condition here. So that's why we pass in the less than as the root.val. The greater than I keep as it is. The greater than, you can see, we passed in from the 5, so I keep it as it is. Alternatively, when you're going to the right-hand side, I want it to be greater than whatever the parent's value is. If I go back here, the right-hand side, so this 10 over here, must be greater than the parent's value, which is 8. And it must be less than whatever was initially passed in. So what was initially passed in? Well, it would be infinity from the parent, from the parent's parent. So that's basically it. This is how you do this question. So now let's go ahead and run it on some sample test cases. And we can see this should be minus infinity. And that's it. Let's go ahead and click submit. And awesome, we have a working solution. So if you look at the time and space for this one, so time complexity, we're just going through basically every single node. You can think of it in terms of that is the total number of nodes in the graph. If it's a fully connected one, then log base 2 of the height. Space complexity, really, it's just a stack space. So if you want to consider that, we can. Otherwise, we're not storing any more data structures here. So basically, it's negligible. Anyways, thanks for watching this video.